Hi, today I'll be going through all the reaction mechanisms that we need to know for the chemistry A-levels. This video is meant to be one where I'll be recapping through the 5 different reaction mechanisms that we need to know. Also, I'll be making videos with more in-depth explanations for some of them, and do let me know in the comments below if there are any types of videos that you want me to make. So for the A-levels, there are 5 reactions that we need to know in total. The first reaction that I'll be going through would be the free radical substitution. So, for this reaction, an alkane will react with a halogen in the presence of UV light or heat in order to produce a halogenoalkane and a hydrogen halide. For this, X represents the halogen. In terms of the observations that we will observe, there are 2 common observations that we will need to know. Firstly, is that when the halogen used is chlorine, we will observe that the greenish-yellow chlorine decolorizes as the reaction proceeds. When the halogen used is bromine, we will similarly observe that the reddish-brown bromine is decolorized. Do remember to memorize these colors. And also, remember that it's very important to know for the A-levels that bromine water is orange in color, while liquid bromine is reddish-brown in color. Do remember this. Moving on. For free radical substitutions, there are basically 3 steps that we need to know. Firstly, would be the initiation stage. In the initiation stage, the halogen bond will be broken in order to form 2 halogen radicals. For my explanation, I'll be using chlorine as an example. So in this case, we will say that the Cl-Cl bond is homolytically broken in order to produce chlorine radicals. So homolytic fission is a type of bond fission where it involves the dissociation of the molecule and 1 electron is then retained by each of the atom in the original molecule. So in this case, we produce 2 chlorine radicals. Also, note that the energy required for the initiation of this comes from UV light or heat, which is why it's one of the conditions that is required for the reaction to take place. Next, the second stage will be propagation. For this, we will be using chlorine and methane as an example. So, these are the propagation steps in the free radical substitution. In the first step, the chlorine radical reacts with an alkane, which is methane in this case, in order to produce a methyl radical. This is what the methyl radical looks like. After this, the methyl radical reacts with another alkane in order to produce the halogenoalkane. Importantly, we need to realize that the chlorine radical is regenerated in the last step. This means that even with just a flash of UV light in the initiation stage, the reaction would still be able to occur and is able to self-sustain once the first chlorine radical is produced. Now, lastly, the third and final stage will be the termination stage. As the reaction moves on, we have more and more radicals that are part of the reaction, right? So in this stage, 2 radicals will collide in order to form a stable product. This means that various different products can be produced at this stage depending on what type of radicals are present. For the case of methane, we'll be able to produce the chlorine atom from 2 chlorine radicals, the CH3Cl molecule from the chlorine radical and methyl radical, and lastly CH3CH3, ethane, from 2 methyl radicals. So basically to recap, in free radical substitution we have 3 stages. Firstly, initiation, where homolytic fission occurs. Second is propagation, and lastly is termination. Moving on, the second reaction that we need to know would be electrophilic addition. In the A-level syllabus, they usually test us the electrophilic addition of halogens to alkenes. So for this, an alkene will react with a halogen in order to produce a halogenoalkane. So the reagents and conditions that we will need for this would basically be either chlorine gas, liquid bromine, or we can say that we use chlorine or bromine dissolved in CCl4, which is an organic solvent. In terms of observations, similar to the previous reaction, we will realize that it depends on the type of halogen that is used. If X is chlorine, we'll say that the greenish-yellow Cl2 is decolorized, and if X is bromine, we'll say that the reddish-brown Br2 is decolorized. Also, it is important to state that this reaction is done at room temperature and in the absence of UV light, in order to prevent free radical substitution from occurring. As I previously mentioned, when there is UV light or heat present, it can lead to the initiation step occurring, hence producing the halogen radical, which will lead to free radical substitution occurring. So now, let me draw the mechanism. For this mechanism, I'll be using Br2 and ethene as an example. In the first step, the electron-rich double bond will attack the bromine atom with a partial positive charge. So why does one of the bromine atoms have a partial positive charge? This is because as the bromine atom approaches the ethene, it will face repulsion due to the electron-rich double bond of ethene. Hence, there will be one bromine which has a partial negative charge and one with a partial positive charge. So after the first step, which is the slow step, will produce a cyclic bromonium ion and a bromine nucleophile. In the second step, which is the fast step, the bromine nucleophile will attack the carbon atom which is just beside the positively charged bromine, and this is the fast step because it's a negatively charged nucleophile attacking a positively charged molecule. This is where we can produce our halogenol alkane. So this is the reaction mechanism for electrophilic addition. Now, the third mechanism that we will need to know would be electrophilic substitution. So in the A-level syllabus, we are mostly tested on electrophilic aromatic substitution, and we will need to know how to draw the mechanism of a halogen, substituting a hydrogen on an aromatic compound, for instance, benzene. So before electrophilic substitution can occur, we need to produce the electrophile. So there are many ways that we can do this. So one of the most common ways of the generation of an electrophile will be using a Lewis acid catalyst. So in this example, I'll be doing that where we use FeBr3, the Lewis acid catalyst, and react it with a bromine molecule, and this will produce FeBr4- and the bromine electrophile. Let me just use bromine and benzene for our example. So once the bromine electrophile is produced, the benzene or your aromatic compound will attack the electrophile. This is a slow step. This will produce a carbocation intermediate. After this carbocation intermediate is produced, in the second step, the negatively charged FeBr4- will attack this carbocation intermediate in order to form FeBr3, HBr, and our product bromobenzene. So you can see electrophilic substitution has occurred because the hydrogen atom is substituted with a bromine atom. Furthermore, as you can see, the catalyst that we use at the start is regenerated in the final step. Now, the fourth reaction mechanism that we will need to know will be nucleophilic substitution. So in our syllabus, we are mainly tested on the nucleophilic substitution of halogenol alkanes. So there are two mechanisms that we will need to know for this. Firstly, Sn1 and secondly, Sn2. Sn1 is basically a unimolecular nucleophilic substitution reaction, which is the reason for the 1 in Sn1. And Sn2 in this case would be the bimolecular nucleophilic substitution reaction. So the first reaction that I'll be going through will be the Sn2 mechanism. Do note that although it's called Sm2, because it's a bimolecular reaction, it's a one-step mechanism. This mechanism is usually for primary halogenol alkanes. I'll start by drawing the primary halogenol alkane. Note that in the Sn2 mechanism, it is very important for us to draw the wedge and the dash in order to show the molecule in 3D. I will be using the hydroxide ion, OH-, as the nucleophile for this example. Now, the nucleophile will attack the partial positively charged carbon atom from the back of the atom, or basically, it will attack from the side opposite to that of the halogen, bromine in this case. This will form a transition state, which is an unstable activated complex, where the entering nucleophile and leaving halogen are partially bonded to the same carbon atom at the same time. Bond breaking and bond forming occurs simultaneously at this step. So basically, the transition state is part of the process and it goes from reactant to product. As you can see, I've said that it's important to draw the wedge and dash. That is because for Sn2 mechanisms, if the original molecule is chiral, the stereochemistry around the carbon would be inverted from the reactant to the product. Now that I've briefly gone through the Sn2 mechanism, let me go through the Sn1 mechanism. So, the Sn1 mechanism is a unimolecular nucleophilic substitution and is a two-step mechanism. This usually occurs for tertiary halogenol alkanes. So in the first step, as you can see, I've drawn a tertiary halogenol alkane. It is where the C-Br bond breaks, which gives us a carbocation intermediate and a bromide ion. The reason this C-Br bond can break like this is because the bond is polar due to the difference in electronegativity between the carbon and bromine atom. So the first step is basically what produces our carbocation. In the second step, we will usually introduce or have a nucleophile that will attack this carbocation in the fast step, because it is a negatively charged nucleophile attacking the positively charged carbocation in order to produce our product. So this is the two-step mechanism Sn1. Now, the fifth and final reaction mechanism that we will need to know will be nucleophilic addition. In our syllabus, we will usually see nucleophilic additions in reactions involving aldehydes or ketones. This is because this reaction usually occurs at the carbonyl group. What do I mean by this? So, as you can see now, I've drawn the carbonyl group, and because the oxygen atom is highly electronegative, you will have a partial negative charge while the carbon has a partial positive charge. If we introduce a nucleophile, The negatively charged nucleophile would tend to attack the partial positively charged carbon, and the reaction will proceed like this. So, generally, we can represent the nucleophilic addition reaction like this, where we have a carbonyl group, which is reacted with a molecule AB, where there's a partial positive and partial negative charge, in order to form the product as I've drawn. So now, for the mechanism, it's basically done in 2 steps. So one of the ways that nucleophilic addition can occur is when I add a carbonyl group, which can either be a ketone or aldehyde, to HCN in the presence of trace KCN, which is basically providing more Cn- nucleophile and cold conditions, about 10 to 20 degrees, we can produce the product cyanohydrine. The reason we use trace KCN is to increase the number of nucleophile. HCN is a weak acid, and when it dissociates, it only produces a very small amount of Cn- ions. Hence, KCN is the catalyst, and KCN, which dissociates in water, will be able to increase the amount of Cn- ions, increasing the amount of nucleophiles. So, for the first step, the Cn- ion acts as a nucleophile and attacks the electron-deficient carbonyl-carbon. The electron pair of the carbon-oxygen pi bond are then repelled towards the electronegative O atom. This results in the formation of an intermediate anion. This is the slow step. So, once we produce our intermediate anion, in the second step, the lone pair on the negatively charged O atom would then attack the undissociated HCN in order to produce our cyanohydrine and also regenerate our catalyst. This is the fast step and completes the reaction. So, we will need to know how to draw these 5 reaction mechanisms for our A-levels, and if you found this video helpful, do consider subscribing to this channel. So now, let me recap the 5 different reaction mechanisms that I've gone through. Firstly, free radical substitution, which is usually for alkanes. Secondly, electrophilic addition, which usually occurs to alkenes. Thirdly, electrophilic substitution, which usually occurs with arenes. Fourth, nucleophilic substitution, which usually occurs with halogenal alkanes with the Sn1 and Sn2 reaction. And lastly, nucleophilic addition, which usually occurs in the presence of carbonyl groups, which is basically the ketone and aldehydes. So do remember that it's very important for us to know how to draw all these 5 reaction mechanisms, as this is commonly tested in the A-levels.